Look at that, perfectly working thrust vector control. I want to make it clear that this project isn't over, but I want to go over the journey so far. I first printed and assembled an updated version of the Omega thrust vector control mount. If you want more details on the design, there's a video linked in the description. This rocket did not fly with the all-rocket avionics bay or air. Instead, it flew on its successor, Trace. I have an entirely different video about it coming soon with all the details. The design for the rocket body and the ejection system was based on the one used in the Cygnus R2 kit, so I'm going to go over it pretty fast. I coupled two 3-inch diameter airframes together. The bottom one was 18 inches long and the top one was 10 inches long. I then set up a coupler bulkhead and glued it into the coupler. Next, I glued a piston bulkhead into a slightly smaller coupler for the piston ejection setup. I'm not going to go over how the charges are made, but here's some test footage of the ejection system. Okay, done with the building. So how exactly does thrust vector control work? When you angle your motor or deflect your thrust, you are creating a small side force on the rocket, and it's pretty easy to calculate. You multiply your thrust, let's say 12 newtons, by the sine of the angle of your motor, let's say 5 degrees. And here you will get about a newton as your side force. The next question is, how do you know how much you need to angle your motor? We do this with what's called a proportional integral derivative or PID controller. First, you have a set point that is translated with your current angle to get an error, and this gets added with the terms P, I, and D to generate the controller output. The output is then sent to the thrust vector control mount, a side force is created, and the new rocket angle is fed back into the controller. Now, the next question is, what exactly are the PID terms? Well, the error is simple, just the set point minus the angle. The integral is integrated with the error times the amount of time spent during one loop of the controller. The derivative is the error minus the previous error, and that's all over the time step. The output itself is the gains Kp, Ki, and Kd times the values previously defined. Great, but how do we find those gains? The answer to that is a little bit more complicated. Still, one of the easiest and most common ways is the Ziegler-Nichols method, where the gains are determined by a profile of oscillation caused by a specific proportional gain. There are several ways to measure oscillation for your rocket. The first way is to set up a custom simulation with a bunch of math. The next method is to fire your rocket on a testbed. This method can be pretty expensive depending on how you execute it, but for good oscillation data, you would need longer burning motors, which are usually more expensive and all require hazmat fees. To be clear, there are much cheaper ways to use a static fire testbed to tune PID values, and I'll be talking about one in a future video. The next option is to pay $300 for MATLAB and the add-ons needed for proper modeling. I ended up using an open source simulator by Cygnus Aerospace Systems, which is just a very fleshed out version of the custom simulator I talked about at first. So a big thanks to him. Just to recap the flight profile before the launch. The rocket uses thrust vector control on the way up, then deploys a parachute at apogee. Pretty simple. So here's the launch.
2, 1. 5, 4, 3, 2, 1.
This didn't work because there was some very extreme mount misalignment at launch. The servo extension cables were also extended by daisy-chaining a bunch of these instead of the proper servo extension cables, so it's likely the computer didn't even have control over the TVC mount. There were a couple design changes I made between flights, mostly to increase the thrust-to-weight ratio. Parts were printed at lower infills, and I used 74mm airframes from Estes instead of the 75mm airframes from Lock. And some metal parts were printed instead.
1.
What went wrong with this flight comes down to how the rocket measures orientation. IMUs don't have any functionality to directly read orientation. Instead, they have accelerometers and gyroscopes. The gyroscopes measure angular velocity. Determining angle with acceleration measurements is quite intuitive and only requires a little bit of trigonometry. For this example, we're going to assume that the IMU is at the angle of x. The IMU has 3 plates to measure acceleration, and we'll label this parallel plate as y. Next, we draw a right triangle that includes gravity and one line perpendicular to the IMU. This is a similar triangle, so this angle here is still x. I'm also going to put a z-plate here measuring the acceleration parallel to the IMU. This makes calculating x very easy. X equals the arctan of z over y. Real quick, let's see how we can calculate x using measurements from the gyroscopes. X is going to be equal to the angular velocity returned in seconds multiplied by your system time loop, 10 Hz for this example, which is added to the previous value of x. This is the process of integrating, but it can be unreliable. Any noise from the sensor is injected into the integration, which quickly forms a bias or drift, making it terrible for long-term measurements. The accelerometer measurements are almost always inaccurate though because the IMU is not still, but it is consistent since gravity does not change. So in this flight, I implemented what's known as a complementary filter where you take percentages of each measurement in a way that complements each other. The only problem is that the filter is very saturated. Basically, relative to the rocket's acceleration, or false gravity, the rocket is completely straight. The way you solve this problem depends on the quality of your IMU. Say you bought a B&O 055 for $30, which from what I found drifts 10 degrees per hour. The solution here is ignore the accelerometers during flight. The drift won't be able to take significant effect during the short flight. If you paid $3 for an MPU 6050 like I did, from my testing, those drift 2 degrees per second. The solution I found for this is calculating the average drift per second on the pad and accounting for it during the angle integration. That's all I really have for this video, and I'm super confident about Flight 3. Anyways, thanks for watching.